Welcome to a screencast on the last few questions from the solutions handout. This is Chapter 11 for Chem 1B, Spring 2017. The first question we didn't get to during class time is question 16. We have a 1 molar solution of sulfurous acid, H₂SO3. It's found to freeze at negative 2.01 degrees Celsius. What is the Van 't Hoff factor for this solution, and what does this mean? Well, we have a freezing point depression situation, so we know the equation that applies to that. We're trying to find I, the Van 't Hoff factor, so we can solve this equation for I, and that's going to equal the difference in freezing point between the pure solution, or between the solution and the pure solvent, water, and then divided by the freezing point depression constant and divided by the molality. Now note we're given molarity, not molality, but if the solution is reasonably dilute, molarity and molality are approximately the same, and we don't have any other information that would allow us to do a direct conversion between molarity and molality, so we're going to have to use that as an approximation. So the freezing point depression is 2.01 degrees Celsius. The constant for water is 1.86 degrees Celsius per molal. And the 1 molal solution is approximately the same concentration as the 1 molar solution. And so when we do that calculation and approximation, we get an I value of 1.08. And probably we should call it about 1.1 because of our approximation we've used. Okay, now that's the Van 't Hoff factor calculated from the information. What does this mean? Well, H₂SO3 is an acid. Acids dissociate into hydrogen ions and whatever the other ion is. So in this case, H₂SO3, we'd expect to dissociate into 2 H+ ions and an SO3 2- ion. Now, if H₂SO3 was a strong acid, it would fully dissociate into these ions, and we'd expect an I Van 't Hoff factor of 3. Well, we actually found the Van 't Hoff factor is about 1.1, so that means that the H₂SO3 does not fully dissociate into H+ and SO3 2-. It only partially does that. We have a partial dissociation, so we have a double arrow, and we'll have an equilibrium situation. More on that in a bit. But what we can say is that the H₂SO3 only partially dissociates in H2O. In other words, it's a weak acid or a weak electrolyte. And in fact, we could even figure out a % dissociation if we wanted to, and that's something we'll do in the future. Okay. One other thing to note, we saw that H₂SO3 in the previous problem has a Van 't Hoff factor that's lower than we might have expected, at least if we were assuming full dissociation. And we've been using the Van 't Hoff factor dealing with ionic compounds. If they're soluble, just say they fully dissociate. It turns out that actual values of Van 't Hoff factor are somewhat less than the ideal, and how much less they are depends upon solution concentration. So, for example, for sucrose, that doesn't dissociate into particles, and so each sucrose molecule makes 1 sucrose molecule in solution, and so the Van 't Hoff factor is 1, and it doesn't really depend upon concentration. But if it's NaCl, ideally it dissociates into 2 pieces, so it has a Van 't Hoff factor of 2. But if the concentration of the solution goes up, the Van 't Hoff factor, the I value, becomes less than 2, and in fact, the more the concentration of the solution goes up, the further below 2 the value becomes. And this is due not that NaCl doesn't dissociate into 2 particles, but the higher the solution concentration, the more likely a positive ion and a negative ion are to be close enough together, essentially paired or stuck together, and therefore not have fully dissociated, or at least at that instant we have those two particles stuck together. And this is called ion pairing, and so actual Van't Hoff factors are typically somewhat less than the ideal, and they become more or less than the ideal, or significantly less than the ideal, the more the concentration goes up. So K2SO4, ideally 3 for its Van't Hoff factor, but you can see as the concentration increases, the Van't Hoff factor becomes progressively less than 3, and just worth noting. Okay, next question to deal with, question 17. An aqueous solution has a normal boiling point of 101.7 degrees Celsius. What's the normal freezing point of this solution? Well, this question was put in specifically for the following reason. Note that we don't have a molality of the solution. In fact, we don't even know what the solution is. Normally, we might figure out boiling points or freezing points or their depression or molality or the Van't Hoff factor if we're given enough information and we can plug into the freezing point or boiling point equations. But here we don't even know what the substance is, much less its molality. How do we deal with that? Well, note, we know the relationship for freezing point depression. We know the relationship for boiling point elevation. And the key thing is, if we have the same solution, which we do here, we're dealing with a solution and we know something about its boiling point, we'd like to find something about its freezing point. Since it's the same solution we're talking about the whole time, if we have one equation and we have a second equation, we can divide one equation by another equation and it's still equal. And here, when we do that, since the molality and the I are the same in both equations, because in both cases it's the same solution, then we can cancel those out, and we're left with delta T sub freezing over delta T boiling is equal to K sub F over K sub B. And K sub F and K sub B, we know, we've used them before, and we now know the boiling point elevation. Therefore, we can solve for the freezing point depression. So using known values, K sub F is 1.86 degrees Celsius per molal, K sub B is 0.516 degrees Celsius per molal. The boiling point elevation was 1.7 degrees Celsius because water boils normally at 100 degrees Celsius, and this solution boils 1.7 degrees higher than that. And when we do the calculation, we get 6.2 degrees Celsius. And then note, that's the delta T. The question asks for the normal freezing point of the solution, so that the 6.2 degrees Celsius is the amount of freezing point depression. Therefore, the actual freezing point of the solution is negative 6.2 degrees Celsius, because that's 6.2 degrees Celsius below the freezing point of the pure solvent, water, and that, of course, freezes at 0 degrees Celsius, at least under normal conditions. And one more. Here we have, this is question 18, we have the vapor pressure of a solution made up of acetone and ethyl acetate, 50 grams of each. And this is at 30 degrees Celsius. We're given the vapor pressure of each substance at 30 degrees Celsius, and we'd like to know what the vapor pressure of the solution is. Well, we know how to do vapor pressure of a solution. We've done that before for a non-volatile solute. But here, acetone has a vapor pressure and ethyl acetate also has a vapor pressure at 30 degrees Celsius. And so neither of these is a non-volatile solute. Neither of them is a non-volatile solvent. Acetone and ethyl acetate both are volatile. So how do we deal with the vapor pressure of a solution if we have two volatile substances mixed together? Well, it's pretty much as simple as saying what's the vapor pressure from the one substance, what's the vapor pressure from the second, and then add them up. So it's just doing our vapor pressure equation, but we do it twice. We do it for each substance because we don't have now a clear solute and solvent, one of which is non-volatile. So the total vapor pressure is the vapor pressure of pure acetone times its mole fraction, plus the vapor pressure of pure ethyl acetate times its mole fraction. Now, of course, to get mole fractions, we need to convert grams of each substance into moles. Since we're given the formula, you should be able to figure out the molar mass and then therefore do the conversion from grams to moles. And acetone, 50 grams, turns out to be 0.861 moles. And ethyl acetate, 50 grams, turns out to be 0.568 moles. So now it's plug into the equation. Vapor pressure of pure acetone is 285 torr. The mole fraction of acetone is the moles of acetone, which is 0.861, divided by the total moles, which is the moles of acetone, 0.861, plus the moles of ethyl acetate, 0.568. That works out to be 1.429 moles total. And then to that, we're going to add the vapor pressure of ethyl acetate, 118 torr, multiplied by the mole fraction of ethyl acetate, which is moles of ethyl acetate, 0.568, divided by total moles, 1.429. Moles, of course, will cancel in the mole fraction, and we'll get a number of torr for the vapor pressure of the acetone part or fraction of the solution, and then similarly for the ethyl acetate part of the solution, and then the total is 219 torr, and that's the total vapor pressure due to the solution, and here again with two volatile substances. Okay, that's it. That's the 3 remaining questions from the solutions handout with the answers worked out.